All right, yep, you too. Alrighty, welcome back to operating systems. So today, inodes, short for index nodes. We left off last time trying to describe how we would store the contents of, or describe the contents of a file. We ended up on an array, but they were too small if we were to store the array on a single block. So, an inode, it technically describes everything about a file, including its content. So this is what your files are actually made up of. They're called an inode, and they are a set size, so they are 128 bytes, and you get to change these in lab 6. So lab 6, you will be populating these fields. So some things in an inode are, well, one, it describes where the contents of a file are, and then all the metadata associated with that file. So it has a mode, has an owner, so like the user and the group that owns that file, some timestamps like when it was created, when it was last modified, when it was last accessed, things like that. The block size count, so how many blocks does this file consume? And then the actual blocks are organized like this because, well, they're pointers to the blocks, yes, but I don't want to waste space for a small file. So before we stored all the pointers on a block, well, if my file is really, really small, if I only need like 10 blocks or 12 blocks or 1, I don't want to use a whole block that's mostly empty. So what it does is there are a whole bunch of pointers here in the structure. Some are called direct blocks, so they point directly to a block. And there are typically, in the case of inodes, there are 12 of these. So the first 12 indexes here will point to the first 12 blocks of the file. If the file is 12 blocks or smaller, it won't use any blocks to store the pointers. If it is a bit bigger, then we get into what we have before, and it's called a single indirect block. So it points to a block. This block is full of pointers, so it is only populated with next pointers, and then those point to other blocks. So that would, with a single indirect block, now in total, if there's 12 direct through single indirect blocks, last time we argued we could point to what, like 2,048 of them. So now we can point to 2,060 in total if you add those two numbers together. Now, if we want to use a file that's even bigger, well, we take a page out of the virtual memory playbook and we use essentially 2 levels of page tables. So there's one pointer here reserved for double indirect that will point to a block full of pointers, and all those pointers point to other blocks that are full of pointers. So it's like 2 levels of page tables. And then finally, there is one pointer reserved for a triple indirect block. So that points to a block full of pointers, which points to a block full of pointers, which points to a block full of pointers. Exactly like 3 levels of page tables. Now, the reason we do that instead of just having a straight triple block or something like that is because we want inodes to be efficient for small files and also have flexibility to support large ones. So the inodes, they hold all of the metadata and pointers to blocks. They are all the inodes for all of the contents of your files are all stored right next to each other on inode blocks. And the idea here is if the file is small enough, we just want to only use direct pointers. We don't want to have to access pointers stored on a block. But if we have a really large file, that's what we have to do. If it's not that large and we only need a single indirect block, we will use that and we will use them in order. If it's too big, if through the combination of the single indirect and the direct block, we need more, then we use the double indirect block, and then if we need to, we use the triple indirect block. And there's also an optimization here. In total, across here, there are 15 pointers. If they are 4 bytes each, that's 60 bytes worth of information. If the content of your file, or in some cases, it's not really used for files, but if the contents of your file, we'll see what I'm air quoting in a little bit, but if the contents are 60 bytes or less, then I can just not point to anything and store the content directly in the space, use it for something else. So that's some optimization we could do. And that's also, if you've ever heard of a small string optimization, it's basically what it does. If a string's small enough, it just uses the pointers to store the string itself instead of actually pointing to data elsewhere. So now if we go back to our inode problem, so here I would tell you in the inode, in that index block, how many direct pointers there are. So typically, this is how an inode is organized. There's 12 direct pointers, one single direct one double indirect, and one triple indirect. And here, like before, if our block size is 8 kilobytes and our pointer to a block is 4 bytes, and we assume the indirect blocks consist of pointers only, then we should be able to argue about the maximum size supported by this. Yeah?
So yeah, I don't know if you already mentioned this, but let's say if a file is too large to be stored by direct pointers, single or double pointers, and we need to use a triple indirect pointer.
Yep.
Would it still store some of the stuff in like direct and single and double?
Yeah, if the file's big enough, we have to use triple. It will only use that if it absolutely has to. So it will fill up the direct ones first, then the single indirect ones first, and the double indirect ones first, and then the triple last. Because you might imagine that's the slowest, right? I'd have to go ahead, read a pointer on a page, then read a pointer on a page, then read a pointer on a page. So yeah, we would use them in order of speed. Yeah?
Why is a block 8 kilobytes?
So a block is 8 kilobytes. It just depends on the hardware. It's typically either 4 or 8. So it just depends on the hardware.
Is it a page then?
No, so sometimes it's the same size of a page, but it doesn't have to be. So it just has to deal with the hardware because the block is the disk block.
Okay, but it's still the same concept that we discussed.
Yes, it's still the same concept. It's just a big hunk of bytes. So just the size might be different. But for argument's sake, if we have to deal with it interacting with virtual memory, we'll just assume it's the same size. But it doesn't have to be. But that's just implementation stuff that you'd have to worry about. All right, well, in this case, if you wanted to figure out the maximum size of a file, you could, like we did before, figure out the number of pointers that could fit on a block. Again, I won't redo that. So it's just the size of a block divided by the size of a pointer, so it's 2 to the 11. So the total number of addressable blocks that we can use for this file are, 12 of them are direct, so they point to a block. Then through the single indirect block, that's one block full of pointers, so that's 2 to the 11. Through the double indirect, that's the same as before, that's 2 to the 11, all to the power of 2, because, they could each point to a separate table. And then through triple, that is 2 to the 11, all to the power of 3. If you want to just approximate stuff, this term dominates all the other ones, so you can just approximate it as being 2 to the 11, all to the power of 3, which is 2 to the 33. So if we want to figure out the maximum size of our file now, it's 2 to the 33 blocks we could point at times the size of a block. So that is 2 to the 47, which is 64 terabytes. So a single file can hold up to 64 terabytes. So everyone, probably good enough for your system? Probably good enough. And if you need to support a file larger than that, then, you could just add a quadruple indirect block, right? And then it's 2 to the 11 times bigger than that. So this is what's actually used, and that's why we can support really, really large files and really small ones efficiently. So now to talk, you might notice that in an inode, there's no such thing as a name. Names are purely in directories, and they are purely for your convenience. So in a directory, there are links to inodes. That's where all of the names are. So a hard link is just a name directly to an inode. So if in my directory I have something like todo.txt, it points directly to an inode. So a directory with an entry, aka a file name, is called a hard link, and a hard link will point to one inode. So this will be fun, where we get to actually look at ls and explain a whole bunch of stuff. And this lecture should be fun because you can tell me to do whatever you want me to do. So if I go here and, let's say I make a file called a.txt, and I say let's say I'm really happy. So the contents of this file is just a with 3 exclamation marks. And if I go here and I do ls, there's some information about this file. So everyone probably knows what this means, right? It's the permissions for the file. So it's like, what can the owner of the file do to it? So it's execute, read, and write. Or, sorry, the other way around. Read, write, execute. So here, the owner of the file, which is me, I can read and write it. And then this is the permissions for the group. There's also a group called John. It can only read it. It can't write it. And then any other user can read it. Anyone know what this number means? Yeah.
So I have a question. What's the first dash for?
The first dash for, it's for special permission bits. So here, we can find a file that actually uses it. So if you use sudo, so they use other weird permission bits. So there's like other things like S and special ones. That's a set user bit, so it'll make sure it always runs it as root, and that's kind of how it works. But that first one there is just for other things that we won't go into. But yeah, anyone know what this number means? Just some boring yeah?
Never mind, I was gonna say, never mind, I think it's gonna be wrong.
What? Take a guess.
It doesn't make sense, so I just don't want to expose myself.
That's okay. Any other guesses?
Number of bytes.
Number of bytes, like the size of the file. So I wrote, what did I write in the file? I wrote A, exclamation mark, exclamation mark, exclamation mark, and then it's a new line. So that's 5, so that's probably this number, right? So that's probably the size of the file. Everyone's seen this every time. What the hell is that? No, still no brave guess?
Is it the number of changes?
Number of changes? Good guess. No, yeah.
Does that have to do with inodes?
Does it have to do with inodes? Absolutely.
Is it the number of pointers then?
Yeah, it's basically the number of references to that inode. So that's what that means. Typically, it will always be 1. Also, what's this mean? That's like when I last changed the file, right? It's like, trust me, this is the last time I changed the file. It was before the due date and everything. Yeah, we'll see why I don't trust that as part of this. But yeah, so this number is the number of, well, we can call it a whole bunch of stuff, the number of hard links to that inode, or the number of references to that inode, whatever you want to call it. So in order to create a hard link, so a hard link is a name to an inode. This means this name is pointing to an inode that's only referenced by one name, which is a.txt. So if I type ln, the ln command will create a hard link by default. So the first argument is a hard link to what inode. So it's the inode that you don't give it an inode number. You tell it a file name, and it will figure out the inode number. So this will say, point a new name that points to the inode given by a.txt, and we can call it b.txt. So if I do this and type ls, there is now a file called b.txt, and that number has gone up. That 1 has now become a 2, because both of these names reference the same inode. And the inode has all of the data about the file, who owns it, when it was last modified, and where the contents of it are. So now if I go and I edit file B now, while I open it, it's the contents of file A. That's all stored on the inode. Then if I modify it and I say, this is my change, and I save it, now if I actually look at the contents of file A, what am I going to see? I'm going to see A, and then this is my change? Yeah. So I'm going to see that because, well, if I edit the file, I'm editing the contents of the file, and I edit it through the inode. If both names point to the same inode, it's the exact same thing. So if I access, doesn't matter if I access a.txt or b.txt, it's the same underlying inode, so it's the same content. And I can see here that, that size updated now, it's 15 for both of them. If you want, you can do ls-li And what li will do is, in the first column here, it will put the inode number. So each inode has an inode number. So if you want to figure out what it is, you do dash I, and then you can see that, okay, these are both pointing to the exact same inode. Yeah?
Why? I mean, I'm assuming that that total 8 is talking about the aggregate number of permissions. Why do you actually care about that?
Sorry, what?
I mean, I don't know, but I'm looking at it, and when it says total 8 and total 4, it looks like that it's counting the total number of permissions. Why would you actually care about that?
Oh, total 8 and total 4?
Yeah. If that's what it is.
It's not the number of permissions, it is. So this is a slightly different file system. It usually makes sense where it's the number of entries. Here, if we do, yeah, there's only 4 entries in this directory. So if I do dash A, that will also show me dot and dot dot. So I can see the inodes for the directories. Directories are represented by inodes too. Let's just ignore that total 4 for now. Yeah,
So is
or
the dot
totally.
in this case a pointer to the direction, the previous, sorry, not the dot dot, is that a pointer to the previous direction? Like, is that the pointer to 28 inodes?
Yeah, so dot is the current directory, right? So the current directory is inode 65577. And then dot dot is the inode number of my parent directory, right? So if I go up to my parent directory, they all should kind of jive with each other. So if I do it here, I'll see that, well, there's a test directory in this directory, and its inode is that. So that tells me what that directory is. And if I do a dot in this directory, since it's the parent of the other one, this number matches this number. Yeah. Yep.
Can you access files directly by traversing to their inode location? Like, can you CD to that actual inode? It doesn't make sense. It's not in the file system, right?
So the inode's what's in the file system. The file system stores inodes. And then the directory just stores name inode pairs, essentially.
Okay. So you can't access the inode without actually having a name, without having a hard link.
Yeah, without having a name. I don't think they allow you to just say, I want to access inode blank. They might.
No.
It would be feasible, but it would be weird because typically we're humans and we use names. Okay, so everyone okay with that? Actually, other weird stuff. So you've been taught up to this point, if I do like RM to something, that deletes something, right? Does that delete the contents? Like if I look at file A now, since they were both hard links, does that delete the contents of file A? Is that just gone now? The answer is no, because all RM does is remove the name. It doesn't delete a damn thing. It never has. It only deletes something if I rm now a.txt, and this is essentially the number of references to that inode, then it would go from 1 to 0. Then it could delete it because it's not used anymore. But by default, all rm does is remove the name. Only deletes it if it goes from 1 to 0. Yeah?
Why does it, like, by delete, do you mean like overwrite the memory? Like, why does it just leave the memory, you just don't have a reference to it anymore?
Yeah, so those blocks are on the hard drive, right? But it probably wouldn't delete them. It would probably just mark it as unused and I can use it for something else, which is a lot faster. And that's also why if you accidentally delete a file, even if it says it's removed and it's deleted, if you act quick enough, you can typically recover it. Because, well, most of the time, your computer's lazy unless you use secure delete. It'll just say, that's not used anymore, and it'll reinitialize it whenever it's reused for something else. And also, this is kind of how everyone's had like a recycling bin or their trash bin or something like that. Well, how that works is if you delete a file, what it'll do is still in that trash bin create a hard link to that inode that you just deleted and hold on to it until 30 days happens, and then it deletes that, that's the last reference, and then it would remove. But it's a lot easier to recover because, well, it doesn't actually get deleted, it still points to that inode. So that's basically how your recycling bin works. Not that complicated, huh? Cool. Operating systems is neat. And yeah, we can just play with the file system all day. So there's also another thing we can create. If there's something called a hard link, there's something called a soft link. So a soft link, the way to think about it, it's not how it actually works, but you can think of a soft link as just a name to a name. So I can create a soft link called b.txt that points to a name to do.txt. It's a little bit of a lie because b.txt would be its own inode and the contents of that would be to do.txt. So there's actually an inode between these two things, but how it works is you think of it as name to a name. Yeah?
So like the name you were printing, the number you were printing before.
Yeah.
That was, you said the number of hard links.
Yeah.
So for example, in this case, if you printed right now, would they both be saying, like what would the entries be?
If I create a soft link?
Yeah.
Yeah, so let's go ahead and do that and see what happens. So if I look at my directory again, I just have a.txt. To create a soft link, I use that ln again, but I use -s. Stands for soft or symbolic link. You might hear both of them. They both mean the same thing. Or in Windows land, this is the same as a shortcut. So shortcuts are name to name, symbolic links name to name. So I will point to the name. In this case, it will be a name, a.txt, and I'll call my new file b.txt. So if I look at it now, this is what it looks like. So it would be its own inode. The number here is number of hard links to that inode. So this is only name to name. So in this case, it is its b.txt is its new inode, but the contents of this inode are just a.txt. It's telling you what it's pointing to. Yeah?
Sorry, so does the inode pointer of btext point to the inode pointer of atext?
No, so like in a.txt, right, its inode holds all the information about when it was created and then the contents of that file. For b.txt, same idea. Its inode holds all of the metadata about that inode, including the name it points to. That's like the contents of it. So in this case, the contents of it are a.txt. And that's also why here in the size is 5, a.txt. So it's the same idea, but it's treated a bit specially because now if I do cat b.txt, my operating system is going to be like, well, I'm not going to show you the contents of the symlink, I'm going to follow them. So if I do cat b.txt, what that will do is, okay, instead of accessing b.txt, it'll know that, oh, no, I should find the inode that a.txt points to, and then it will find this inode and then print that. So it's a bit of an indirect way to do that. Yeah?
Like, in terms of like you were saying inodes are pointers to files, right? Or am I misunderstanding?
Inodes hold the contents of files. Like the pointing is pointing to the contents of that file. Yeah. So now, well, if I have a symlink, right, if I removed a.txt before, I would still have that inode. But now, if I remove a.txt and look now, things look unhappy. Because now, well, a.txt does not exist, right? Now I'm going to get a weird error message. Because if I cat b.txt, does b.txt exist? Absolutely, just the name it refers to, a.txt, doesn't exist. So you will get a confusing error message if you try and cat that says b.txt, no such file or directory, because it followed the symlink but still used the name b.txt. I guess they thought it was clearer than just saying a.txt not found when you tried to do b.txt. I don't know, but Anyone see any other weird things we could do with that? If it's named to a name, we like infinite loops. Could we make an infinite loop out of this? Yeah.
Can you make a cycle?
Yeah, can we make a cycle? So can we make a symlink called a.txt that points to b.txt? Well, let's see how smart our operating system is. Hey, let's see if anyone ever thought of that. So we will create a file called a.txt that points to b.txt. So if we do that, it looks slightly unhappy, but now we have a.txt points to b.txt, b.txt points to a.txt. So if I cat b.txt again, what's going to happen? Is this going to be another fun thing to do to first years again? So let's see what happens. Too many levels of symbolic links. Damn, they outsmarted us. So question might be, who outsmarted us? Did the kernel outsmart us, or did whoever wrote cat outsmart us? How would we figure that out? Yeah? No? Yeah?
Instead of pointing A to B, can you just point A to like a C file, like a third file?
So we're going to try and outsmart it. So you want to point A. So let's remove A. Whoops. So we want A to point to a C, and then C to point to B.
Like C be like a operator, like file.
Oh, you want it to be a real file?
Yeah.
Oh, if it's a real file, then it should be fine, right? So if we have c.txt, so now it should resolve, right? If we cat, what's the most indirect one? B? Then it will follow, give us C, because B, well, that's a symbolic link to A, then it finds A, that's a symbolic link to C, and then C is an actual one that points to an inode, we'll use that one. So that's fine. Let's remove this. All right, so how do we figure out who's the smart one, cat or the kernel? Yeah.
I think logically it would make sense to be the kernel, because otherwise every single command will require the
Yeah, logically it makes sense that it's the kernel. Otherwise, every single other command would have to recognize this and program against it to not infinite loop. How would I check if the kernel did it or not? strace, right? I can just strace the thing. So if I strace, that will give me evidence as to who did what. So cat b.txt, too many levels of symbolic links, so we strace them. So we strace it. So this is printing to standard error, too many levels of indirection. Let's see where that came from. So here, so all that stuff, the locale stuff, is just to print it off in whatever language you want. It seemed to fail a whole bunch of times, so it's just going to use default. Reads, so that's all printing stuff. This is also the error message, and oh, there's that error message. That's just one open b.txt. I got an eloop error, so that was from the kernel. So the kernel protected us. We don't have to write that or handle this case in all our programs. Our good old buddy, the kernel, does it for us. So that's good for us. We don't have to argue about stupid symbolic links, and symbolic links are really fun. So anything else we want to do with this? Anything else we want to break? Should be more or less okay. I think we broke. Oh, want me to show you something that you shouldn't do and why I don't trust you guys with timestamps? Yeah, so like I said, on the inode, so here, let's say c.txt is my assignment. So has anyone ever used this touch command? What's touch do? Makes a file. So it does make a file if it doesn't exist, but what it'll actually do, its actual intended purpose, is if I touch c.txt, So this is the last time I modified it, 38 or 37. What that will do is update that last time I modify it. So it touches the file and says I just modified it. Even if I don't make any changes, it updates that timestamp. And that timestamp, well, I mean, it's just my most recent update to it, right? So I can tell you, if I give you this file, it has this timestamp on it, and I can tell you that I definitely submitted it before the due date tomorrow. It's today's date, right? So, touch. It will also let you do more fun things. So it will also let you change that date to whatever you want. So if I just do /d and change it to 1980, which is provably not today, and say I did it on Christmas Day at 6 a.m., I was definitely alive and awake at that time, and I can touch it and then look at it again, and boom. So I definitely did it before I was alive. Trust me, bro, I definitely did that. So that is why I may or may not know someone that handed in their assignment this way and got away with it. But this is why I do not trust timestamps on files, because you can modify them all you want. There's nothing to verify it. You just change it. So say it with me. I promise not to do that in other courses. All right, so I did not show you that. I don't know why I do these things, but yeah, I teach you all sorts of terrible things here. Yeah.
How can we change the year but not the time, or is that just not showing?
Yeah, so the time's just not showing. So if it's too long in the past, it just doesn't show the time, it shows the year. If I wanted to, I mean, if I change it to something more recent, let's say Christmas Day this year, well, I think it doesn't show the time unless it's the same day. Because even if I put it for tomorrow, yeah, it still doesn't say. It only says the time if it's the same day as today. So if I did it the same day, that's just how LS is. So if I did this, it should say 6 a.m., which clearly I was actually awake at 6 a.m., but you guys definitely weren't. And I definitely didn't make this at 6 a.m. All right, any other fun things we want to do with this? I taught you bad things. So, and yeah, this applies to Windows too. So if we did something like this, so by default, if you touch a name that doesn't exist, it will create an empty file with that name and update the timestamp to that. So if I touch to-do.txt, create a hard link to that same inode for that empty file called b.txt, and then I create a symlink to to-do.txt called c.txt. Well, then I can access that empty file through c, b, or to-do.txt. If I do this move command, so move, you might think it's called move because it moves a file. Well, it doesn't do that. The move command, what it really does is just rename the name. It doesn't do anything with the inode, doesn't move the contents or anything like that. So if I do move to-do.txt, b.txt, or d.txt, it just changes the name. So that name still points to that original inode. And then if I remove b.txt, well, then I should break that link or after I move that name, then I can't access that file through c.txt because it's just a symlink. But I could access it through b.txt. And if I remove b.txt, well, then there's only one thing pointing to that original inode, and that is d.txt. So we should be able to answer how the file system looks like before and after the move and rm commands here. So if I look before the move, again, symlinks, easiest way to think of them is name to name. Really, there's an inode in the middle here because it needs to store the name somewhere. But right before this move, I have one inode, let's call it inode1, that gets created from the touch. b.txt and todo.txt are hard links to that same inode, and then c.txt is a symlink to do.txt. Yeah?
Sorry, so the difference between the soft link and the hard link, is it just that the symbol that is a soft link to something else, its inode points to that symbol?
Yeah, so symbolic link, just think of it as name to name.
And then the hard link is that its inode points to the file?
So hard link is name to inode. And whenever you try to access a name, it will always follow whatever to get to an inode. If it's a hard link, it'll get to the inode directly. If you try and cat a symlink, then the kernel is going to follow all the symlinks until it eventually gets to an inode. So, everyone okay with this? This is the state of things? Yeah?
Sorry, so then what's the advantage of like a soft link versus a hard link?
So soft links, the reason why we would use them is because, well, maybe this todo.txt, if it pointed to an inode, then if c.txt was also a hard link to that inode, and say I actually removed todo.txt and then recreated it later, so now it's pointing to a different inode, I have now broken that c.txt, right? It points to the old one, not the new one, and I want it to point to the new one. So generally, so if I know that the inode might change, and I don't really care, I would use a symbolic link. Most web servers and things are set up to be symbolic links so that it's just a name and it resolves it. So sometimes too, your Python executable, the Python you're running, is actually a symbolic link. And there might be multiple Python executables on your computer, but Python will be a symbolic link to one of those. And then if they want to change the default version of Python, they just change that symbolic link to point to the newer version. So that's typically what they're used. They're a bit more indirect, so they'll survive updates better. All right, so everyone okay with this before the move command? So if we do move, what that will really do is just actually get rid of this link from todo.txt to that inode. So c.txt will still point to that name, but now in this directory, todo.txt does no longer exist. We renamed it. Move should actually be called rename, but if there was an rn and rm command, you would and one rename something and one remove something, probably not a good idea, so that's why they call it move, just so you don't accidentally delete things. So it just renames that hard link before todo.txt that pointed to node 1 to d.txt that still points to node 1. Now, if we remove b.txt, that means we only have one thing pointing to that inode anymore. And now if we try to access c.txt, that will not resolve to an inode eventually, and it will say file not found. So everyone okay with that? Yeah?
Does move just make a new symbolic
Nope.
like hard link to the inode it was pointing to?
No, move just renames the name. So it doesn't do anything to that inode. So as soon as I do move todo.txt, d.txt, it just renames todo.txt to d.txt in that directory. Doesn't do anything with the inode at all. So yeah, should more accurately be called rename. Yeah?
Can we use move and move on soft links?
Yeah, you can use move on soft links. That'll just rename the c.txt to whatever you want. So yeah, you can use move on soft links.
And it will still point to the exact same.
Yeah, so it'll still point to do.txt, yeah. All right, so on Unix, Mac OS, Linux, everything is a file. Directories are files of type directory instead of regular files. So additional file types are regular file, a block device, that's how it represents a hard drive. a block device, so I can only access it blocks at a time. You can have name pipe, so you can have a file that is a type pipe. Sockets look like files. They have an inode. It doesn't have any content, but it has the type socket. And directory inodes, they do not store pointers to data blocks or anything like that. The content of a directory, it's like a file, it's just formatted in a special way. So directories, especially you'll create a directory from scratch in Lab 6, but directories, they are just essentially storing a whole bunch of tuples. They just store name to inode pairs, and that's all a directory stores. So if I go back to here, if I look at this directory and I look at it all, whoops. So the contents of the directory, like if it was an actual file, well, if I accessed it as a file, it would have all of the name inode pairs. So there would be an entry called dot with this inode, dot dot paired with this inode, a.txt paired with this inode, b.txt paired with this inode, and c.txt paired with this inode. So that is all a directory is. It's not that special aside from just giving an inode a name. So now we should be able to answer all sorts of things now. So what data is stored in an inode? So let's go through it fairly quick. So is the file name stored in an inode? No, file names are only stored in a directory, right? The inode itself just has metadata and points to the contents of the file. Does an inode know which directory it's in? No, it's only in that directory. If you need to look up where an inode is, you'd have to go throughout your entire file system. Does an inode know the size of the file? Yes, that is stored on the inode itself. Does it know the type of the file? Yes, that is stored on the inode itself. Does an inode know the number of soft links to a file? No, just name to name. Does it know the location of the soft links? Absolutely not. Does it know the number of hard links to that file? Turns out it does. That information needs to be somewhere. So it actually stores the number of links to that inode on the inode itself. So if you use the stat command, there's also a stat system call that will show you a whole bunch of information about the inode, including the file name, which is not on the inode, but the rest of the stuff is on the inode. So it tells you the size of the file, so in this case it's 10 bytes, how many blocks. Annoyingly, when you get into Lab 6, this number of blocks is really, really, really stupid. So the number of blocks is the number of fixed size blocks of size, let's recalculate it, of size 512. So the number of blocks there are the number of size 512 blocks there are. It's just hard-coded at 512. Don't ask me why. So this file will take up an I/O block. So this is, in this case, it's the same as the virtual memory page size. So the contents of the file takes up exactly one block, one I/O block, which is 8 fixed size blocks of 512, but it's one I/O block, and that's as small as a regular file can be. So it'll tell me what device it's on, its inode number, then the number of links there are to this inode. So that would change there. And then it also has the metadata, who owns it, when it was last accessed. Some other file systems will have more content, but there's like access, modify, and change. You might be like, what the hell is the difference between modify and change? One of them is the last time the contents of the file was changed, and the other one is the last time that inode was changed. So two different things. I forget which one's which. I think modify is the contents and change is the inode itself, but don't quote me on that one. And birth is supposed to be whenever this inode was created. So the number of links to that file, that is stored on the inode itself. not the location of the hard links, only in the directories. Access rights are stored on the inode. Timestamps are stored on the inode. File contents are not stored on the inode. It's pointers to the contents on the disk. And then an ordered list of data blocks. Yes, those are the pointers to the data block, so that is what is stored on the inode. So, going through all that, these are all the answers. There's a sometimes here for the file contents. As you will see, for symlinks, if we go back and we do a stat on a symlink, we'll see that, oh, this one does take an IO block. Okay, weird non-default file system. But for you, for your file system, here, if like the contents of the file of a symlink is like the name, so it'd be like b.txt. There is an optimization for symlinks on the file system you're going to use is if they are smaller than 60 bytes, they're stored wherever the pointers are stored, and the string's just stored right there. So it uses that ordered list of data blocks to store the actual string itself as that optimization, but that is only an optimization for symlinks, so that's why it says sometimes. So, other things we can do, we can have a file system cache to speed up writing to disk. Writing data to a disk is slow, so what you can do is just, instead of writing it back out to disk, you can actually cache a file block in main memory. There's something called a file system cache, because, well, likely if you are modifying that block, you might be likely to modify it again. That's called temporal locality. Or I might actually just like preload the next sequential blocks, and that means spatial locality. So if I'm accessing an array, it's likely I'm going to access the next element, so I should probably just load it in and cache it. So there is going to be a kernel thread or daemon that writes data changes periodically to disk whenever it's otherwise idle, otherwise it won't do it. This might be sometimes if you plug in a USB drive that you know is really slow and copy a Linux ISO to it that's gigabytes, it might finish really, really quick, but that's because it all got cached and it didn't actually write to the device. So if I want to force writing to a device, I can use a system call or command that does the system call called flush or sync, and that will trigger all of the writes to happen. Same for this idea of buffering and stuff, same with printf, that's why I use fflush sometimes to flush out printf, so it actually does the write system call. Other little things we can do in the file system, something called a journaling file system. So if I delete a file on Unix, it involves 3 steps: removing its entry from the directory, that name inode pair, releasing that inode from the pool of free inodes, so this inode is no longer used, and then all of the disk blocks that file used, I get to free them all. You could crash or pull out the power between any one of these steps, which is leading to a storage leak. If it crashes here, then I release that inode, I can reuse that inode, but now all of those disk blocks are marked as used, and I can't reuse them anymore. So basically what a journaling file system does is, before it does all these, it writes an entry that says what it's about to do, and only deletes it after it's done all 3 steps, so that way we can recover. If we crash between any one of those, we read the journal, see everything we were in the middle of doing, and then go back, replay the steps, make sure everything is consistent. So that is a journaling file system. That's the default thing Apple does now to make sure that, hey, your file system is actually consistent. So we can wrap it up. Inodes are a hybrid allocation strategy, much better flexibility over contiguous linked file allocation table or indexed. And on Linux, everything's a file. Names in a directory can be hard or soft.